Collisions in two dimensions. The College Board AP Physics 1 exam only requires students to set up the equations properly and be able to discuss how changing the mass, speed, or angle of the problem affects the other quantities. The full numerical solution, however, is shown in this topic for completeness.
Momentum vectors, like all vectors, can be expressed in terms of component vectors relative to a reference frame. So example, if we have a reference frame here, x and y, we can take a momentum vector that is at this angle here and express it in terms of px and py. And here we're just showing the magnitudes of these components. This will also, of course, apply to 3 dimensions, but we'll just do 2 for this chapter. So that means the momentum conservation equation, where your initial momentum equals your final momentum, can be solved independently for each component. So we have p sub x equals p prime sub x, and py equals p prime sub y. Consider a system of 2 objects moving in random directions in a 2-dimensional plane and then colliding. We'll assume there are no external forces acting on the system, so momentum will be conserved. Since there is no absolute reference frame, we're free to choose one that works for us. So in this case, we'll take this as our frame, where the y-axis is in this direction, and the x we're going to line up with the velocity of mass 1. So here's our 2 objects, and we're going to assume that mass 2 is at rest just to make the problem easier. And here's mass 1, where we've lined up the reference frame, the x direction, in the same direction as mass 1's velocity. Furthermore, we're not going to assume a head-on collision, because after the collision, put a little wavy line here, m1 is going to move off in that direction. And the problem is, what's going to be the momentum of mass 2? We know that momentum must be conserved in both the x and the y directions. Initially, there is 0 momentum in the y direction. We just have mass 1 moving in the x direction. So therefore, the final momentum in the y direction must also be 0. The momentum that m1 has in the beginning will then be shared between the 2 masses after the collision. It will not be shared equally. It will depend on the masses and also the separation angle. See this angle here, m1 makes an angle with respect to x, and then m2 we're anticipating will move something like that. Let's sketch in the vectors. Mass 1 we know moves up in that direction, so we know it has a component of momentum in this direction, which we write over here, and it also has a component in the y direction, and that's what this guy is right here. So now let's look what m2 has to do. Well, first of all, it has to make up some of this momentum. All right, this is your initial total momentum, so my final momentum has to be the same length. So this piece here is going to be due to this object here, mass 2. We also know that since there's no initial y momentum, the momentum of object 1, which is in the up direction, must be exactly canceled out by the momentum of object 2. So here's your x components, here's your y components. Let's take these blue lines here, which represent the momentum of mass 2. We add them together. Here's the horizontal component, here's the vertical component, and right here is going to be the final momentum vector for mass 2. And if you remember from just a slide back, we kind of guessed that it would move off in this direction. Educated guess. If you've ever played billiards, you would see if you hit a ball and the one ball goes this way, the other guy typically goes like that. Let's switch from vector analysis to some algebra to find the momentum, which is the magnitude and direction that m2, which is the bowling pin, leaves with after the collision. So here's the problem statement. You have a momentum here of m1, and then you have the momentum of m1 after the collision, and the angle it takes off with respect to the x-axis. The nice thing here is we don't have to worry about the masses because we're just calculating momentum, and the problem is find the final momentum of the pin. An excellent way to start any physics problem is with a nice sketch, which we have, and then list your givens. We know that mass 2 is at rest, so it has no momentum either in the x direction or the y direction. Mass 1 has a momentum in the x direction, nothing in the y. We come over here, here's our given, and we right away resolve this vector into its x and y components. The x component is going to be the hypotenuse, which is 12 times cosine of the angle here, 60 degrees. The y component is going to involve the sine function. So that's what we have here. So now we have our final momentum of the bowling ball broken down into its x and y components. What we want to find is the momentum of the pin, and that's this vector right here. Now if we draw a right triangle there, we know that this is going to be P2x and this is P2y. So to find the magnitude of the hypotenuse, we just use Pythagoras here. And you can see how we have the primes indicating this is the final momentum. To find the angle theta, we just use the arctan function. It's equal to this side, the magnitude of this side, opposite, over adjacent. And the adjacent side is the x component. And here we have the equation we're going to use to find theta. We'll use the conservation of momentum in the x and y directions. Let's start with x. We have the initial momentum in the x plane for both objects equals the final momentum. Again, don't put any numbers in until you have your variable isolated. We want to find p prime of 2x. So we get that over to the left, everybody else is on the right. Now you can put the numbers in. We have the initial momentum of object 1 in the x direction is 20 kilogram meters per second. There is no momentum in the y direction. And here's the final momentum of object 1 in the x direction, 12 cosine 60. Keep the units outside here just so we don't have to put them next to each number. And we find that p prime 2x is 14.0 kilogram meters per second. Now, in the y direction, very similar, except here we're solving for p prime 2y. We isolate the variable. We substitute in our numbers. And again, that's why it was handy to have a section that showed our given. And of course, we derive this by basically using a variant of Pythagoras. Add the numbers, and we have p2 prime y is negative 10.4 kilogram meters per second. And that makes sense. You can see how the x component is positive and the y component is going to be negative as it's pointing down. We have the x and y components of the final momentum of object 2, the bowling pin. So we go to Pythagoras to find the magnitude of the vector right here. That's where the momentum is directed. You just square these terms and take the square root. Notice how we don't care about the negative sign here. We just square it. And we get a final momentum, magnitude of momentum for the bowling pin of 17.4 kilogram meters per second. Now we want to find the angle theta. That is equal to tan inverse of the momentum in the y direction divided by the momentum in the x direction. We put the numbers in here, and here we see the angle will come out to be negative. The tangent function is negative in the fourth quadrant, and we get an angle of negative 36.6 degrees. Or we could also say it is 36.6 degrees south of the x-axis. Or we could have a picture and just point to the angle and put the number. That's also a good way of doing it. Anything that makes it clear to whoever is working with you. Start with listing the given quantities. And that's what we have here. Theta prime ball, and we're going to rename that theta 1. Just again, instead of writing ball all the time, we'll just write 1, is 53.1 degrees. Theta prime pin, and we'll rename the pin object 2. Its theta is 30 degrees, and P2 prime is 18 kilogram meters per second. I'm not going to worry about negative or positive here because we're going to take advantage of the sketches and figure out which way the velocities and momentums are. And we want to find all the way over here the velocity of the ball, which we will call V1. We're actually going to work this problem backwards in that we're given the after conditions and we need to find the before. So a good place to start is conservation of momentum in the x and y directions, as this is a two-dimensional problem. In the x direction, we have our initial velocities of p1 and p2 will equal the final momenta. Initial momenta, final momenta. P2x the initial momentum of the pin is 0, so that cancels out right away. So we're left with, here's our conservation of momentum in the x direction. The y direction, similar equation, except instead of x we put y. Now what's our initial momentum in the y direction? Well, this ball isn't, the pin isn't moving, and the ball is only moving in the x direction. So these both get replaced by 0. We get p1y prime plus p2y prime equals 0. And we come up with this relationship for the final momenta in the y direction. Now remember, we have to find the velocity of this ball. So all we have to do, and take a couple more slides, is find the initial momentum of this ball through conservation of momentum, then divide it by the mass of the ball, and we're all done. It's still going to take a little while though. We need to find p1x, because once we get that, we can divide that by the mass and find the velocity of the bowling ball. And that will be p1 prime x plus p2 prime x. So let's take these quantities over here and resolve them into their x components. First of all, for the pin, which is p2, the hypotenuse of this is 18. It makes a right triangle like this. So when we want to find p1, p2 prime x, it's just 18 times the cosine of 30, and we get p prime 2x is 15.6. We're going to leave the units off here. We'll bring them back at the end because we're doing so much math. Now, to find p1 prime 1x up here, we don't have a hypotenuse. All we have is an angle. So what we can do is we can just take this right triangle, and the tangent of the angle 53.1 is equal to the opposite side, which is p prime 1y, divided by the adjacent p prime 1x, and we wind up with p prime 1x is 0.751 p prime 1y. Okay, that's great. We've got this term over here. Now p prime 1x is now expressed in terms of p prime 1y. So our next step is to find that value. In order to find p prime 1y, we go back 2 slides, and you can go ahead and check it. Go back 2 slides where we did conservation of momentum and came up with this. So what do we have here? We have, here's p2, it's 18, okay, so it's minus 18, and we want to take the sine of this angle here. So in this case we'll call it negative 30, and then we take negative 18 sine negative 30 equals 9. Now that makes sense to us because we know that p prime 1y is up in the positive direction. So even if we just use 30 here, we would have known to switch it and make sure that we have a positive momentum here for p prime 1y. Now go back to the previous slide where we had p prime 1x was 0.751 times p prime 1y. We carry out the multiplication. Now I can put the number in right there, and you get 6.76. We now know p prime 1x, and we know p prime 2x from the previous page. We substitute the numbers in. Here 6.76 comes here. We found 15.6 on the previous page, and we now know that p1x, which also is the total momentum here, because you have no momentum in the y direction, is 22.4 kilogram meters per second. Told you we'd put the units back in at the end. Now we need to find the velocity of the bowling ball. That's p1 over the mass of the bowling ball. 22.4 comes over here. The mass of the bowling ball is 5 kilograms. And we wind up with the final answer that the initial velocity of the bowling ball was 4.5 meters per second in the positive direction.
A common perfect inelastic collision is where 2 cars collide and stick at an intersection. The cars are traveling along paths that are perpendicular just prior to the collision. So here's one car, momentum in this direction. Here's the other car. They hit each other and stick together, and they take off at an angle here, p prime, theta. We have our xy axis over here, and your after collision, you have a momentum in the x direction and also in the y direction. To find the total momentum, you use the Pythagorean theorem to find p prime, and that's right over here. And then your final velocity would be p prime divided by the combined mass of the two cars or objects, and you use tan inverse to find the angle theta. Now, going back to the top here, what has to be conserved? It has to be conserved in both the x direction and the y direction. So p1x has to equal px prime, and in the y direction, p2y has to equal p prime y.
Let's look at an explosion in 2 dimensions. We have a black object right here, which will explode into 3 pieces, blue, red, and green. We want to determine the momentum of the third piece right here, given the momentum of piece 1 and piece 2. Can you see why the third piece moves the way it is shown? Now earlier we talked briefly about how if you have 3 or more objects colliding, it's almost impossible to predict what happens, and now here we have 3 pieces. Well, the difference is we're telling you the initial momentum is 0, giving the values of P2 and P1, and we're only asking for P3, so that's okay. So let's get back here. Why is the third piece moving in that direction? During an explosion, the total momentum is unchanged. There are no external forces acting on the system. We do have the potential energy of this box changing into kinetic energy, but that's internal to our system. By Newton's third law, the forces that occur between the particles within the object will add up to 0, so they don't affect the momentum. If the initial momentum is 0, which it is, the final momentum has to be 0. So the third piece of this must have equal and opposite momentum to the sum of the other 2 pieces. So that's what's sketched in here. Here's the momentum of P prime 1 after the explosion, and here's an equal and opposite right down there. Here's the momentum of P2 after the explosion. Here's its equal and opposite component. So when I add these 2 vectorially, I get P3 prime moving off in this direction. We have the initial momentum of this object in the center is 0. So Px has to equal Py, which equals 0. It then explodes, and we know the momentum of P prime 2 and P prime 1. P prime 1 is only in the x direction, so right over here it shows that its y direction is 0. P2 prime has no momentum in the x direction, so that's equal to 0. Now let's come on over here. After the explosion, momentum is conserved in the x direction, also in the y direction. So I take my term here where P prime 1y equals 0, look right here, and this term cancels out, and then I come up over, just follow the line, and I have P prime 3y is negative P prime 2y. I'm going to do a similar thing for the x direction. I have P prime of 2x is equal to 0, so this term goes out. Then I come on over and I find that P prime of 3x is going to be negative P prime of 1x. So now I can substitute my values in for P prime 3. That's just P prime 3x quantity squared plus P prime 3y, the quantity squared, take the square root. I make these substitutions here, right, because I don't know what these guys are, and I have P prime 1x quantity squared and P prime 2y quantity squared. Again, we don't worry about the negative signs, they're going to cancel out. Here's the only tricky part. You're used to tangent being y over x. Then how come I have x over y in this case? Well, you have to go back to the sketch. That's why it's so important to draw sketches. In this case, I'm trying to find this angle theta relative to the negative y direction. I could also have asked you to find this theta, but here we're finding this one. So when I take the arc tan, this side, the opposite side, happens to be P prime 2x. So that's why you have the x there. The adjacent is in the y direction. So the subscripts are a little different than what you used to, and I did that on purpose. The whole idea is for math to serve physics and not the other way around. A golf ball down here collides elastically with a very rigid wall and moves off in that direction. We're going to assume that there's no internal energy change of the wall doesn't move, it's very massive. Earlier we talked about the one-dimensional case, where if an object hit the wall like this, a light object, it would bounce back, keeping the same magnitude of the velocity, just in the opposite direction. In this case, we're coming at an angle, and since we have an elastic collision, this is very similar to light rays bouncing off a mirror. This angle here, the angle of incidence, is going to equal the rebound angle, this red angle here. So given these constraints, what can we say about the momenta in the x and the y directions? The solid lines show the actual momentum of the ball. So here's P prime, and the dashed lines show the resolution into the x and y components. We're not considering the wall to be part of the system here, and we have an external force that's being applied to the ball in order to reverse its direction. Now, what is that force? Well, whenever you strike something, there's something called the normal force. We did that earlier in dynamics, which is always perpendicular to the surface that you're resting upon or striking. So we have a normal force that's changing the direction of the ball. Since we're assuming an elastic collision, the ball bounces off the wall with the same speed that it struck the wall with. There's no loss of kinetic energy. Of course, there is, but it's going to be so slight we're going to ignore it. So if the velocity is the same and the mass is the same, excuse me, not the velocity, the speed, the magnitude of the initial momentum and the final momentum has to be equal. So here's the final momentum, it equals the initial momentum, so we'll get rid of the magnitude and vector signs and just say that P prime, there, the magnitude there, is equal to P. With the help of the sketch, so we get the right signs for all our components of the momentum, we're going to first look at Px, the initial momentum in the x direction. Well, it's to the right. You can see how Py plus Px is this initial vector. So Px is going to be P cosine theta, Py will be P sine theta, and both are positive because they're moving in the positive directions. That's positive for x, that's positive for y. Now let's look at the final momentum. Px prime this time is moving in the negative direction. So that will be minus P prime cosine theta, or just minus P cosine theta, because earlier we said that P prime is equal to P. P prime y, the momentum in the y direction, will be P prime sine theta. Again, the final momentum is equal to the initial momentum, so we don't need the prime sign. So here's what we have. Here's our values for Px and Py, and for P prime x and P prime y. Now we're going to apply the impulse momentum theorem in 2 dimensions. The wall is exerting the external force in this case, and it's a normal force. So in the x direction, we get f sub x delta t is equal to the differences in the x momentum, and we get negative 2p cosine theta. Now look at the y direction. We have p sine theta minus p sine theta. We get 0. What is this telling us? These 2 equations tell us that the momentum is conserved in the y direction, but it is not conserved in the x direction. The only force we have here, once the ball hits the wall, is the normal force, which is perpendicular to the contact point here. So we have an external force in the x direction, so you would expect momentum not to be conserved, and it in fact is not. There is no external force in the y direction, so momentum is conserved. Mathematically, again, the initial and final momentum in the y direction are the same and subtract out. That's right here. The initial and final momentum in the x direction are equal in magnitude, but opposite in direction. So they add up to a value in the negative x direction, and that tells you which direction the ball moves because of the wall. It's in the negative x direction.